Hi guys, I hope you're all doing well. Today we're going to look at the ordinary level questions that were due last week, March 31st. I'm deliberately releasing the videos a few days later to give everyone a chance to have tried them. Now, if you haven't tried these questions, stop watching the video. It's pointless watching it until you've tried them yourself. Okay, that's how you kind of get the learning value from it. And even if you try to make a hanes of it, send me what you have and see how to improve it the next time. That's the trick. Alright, so without further ado, let's get cracking. Both of these were theory based this week. I didn't put in any experimental questions. So they're both to do with forces and mechanics, which again is a really core area of the course. So if you're looking to get across the line, get a decent grade, making sure you're solid on mechanics is a great way to do that. Alright, so we've got Sir Isaac Newton was an English mathematician and physicist, widely recognised as one of the most influential scientists of all time. Newton's first law of motion Newton's first law of motion states that a body remains at rest or moving at a constant velocity unless an unbalanced external force acts on it. So, first part that we were asked to do. A block weighs 400 newtons. A crane lifts the block so that it moves upward with constant velocity. Use Newton's first law of motion to find the force that the crane puts on the block. Okay, well the crane's going to need to apply an equal and upward force, so it's going to also need to apply 400 newtons if it's going to get it moving upward at zero acceleration. Using Newton's second law of motion states that the force of an object is proportional to its rate of change of momentum. Calculate the resultant force on this object here, and in what direction does it act, and then they're going to ask us to calculate the acceleration. Okay, so we've got three forces acting, 6 newtons pulling it to the left, and a total of 8 newtons pulling it to the right. So the resultant force here is going to be a total of 8 minus 6, so it's going to be 2 newtons in over towards the right as you look at the page. Calculate the acceleration. Okay, well the force is equal to mass times acceleration. We know the force, we know the mass of the object, we just don't know the acceleration, so let's rearrange this. Just bring the m across. F over m will give us our A. So the force is 2 newtons divided by the mass of 9 kgs will give us our acceleration. 2 divided by 9, 0.2 recurring meters per second squared. Always don't forget your units or else you're just throwing away marks. Make sure you give your unit for your final answer as you go. Okay, state Newton's third law of motion and use Newton's third law to explain how a rocket takes off. A label diagram might help in your answer. So Newton's third law states that for every action there is an equal and opposite reaction, or that if a body exerts a force, if a body A exerts a force on body B will also exert an equal and opposite force on body A. So how does it help the rocket to launch? When you've got a rocket launching, what it does is it expels a huge cloud of gas, and when it combusts, there's a huge plume of gas coming out, and the gas exerts a force on the rocket, just as the rocket exerts a force on the gas, which causes it to take off and move in an upward direction. Okay, so the first sections were not too shabby, but I think we're getting to harder stuff now. So what have we got? A car of mass 700 kilograms is at rest. It accelerates at a constant rate for 6 seconds until it's traveling at a velocity of 18 meters per second. Calculate the kinetic energy of the car when it is traveling at 18 meters per second. Okay, so they're going to want us to solve at this in a moment, but first we just need to get the kinetic energy of the car, and the kinetic energy of the car is equal. And again, start off by just writing out the equation. It's in the logbooks, you don't have to memorize it, but just showing that you can apply the formula gets you started, So the kinetic energy formula is half the mass times velocity squared. And now you can sub in our values. Half the mass of the car is 700 kgs. The velocity is 18 meters per second. They've not laid any traps here. The units all make sense. They're on System International. So all we got to do is go 18 squared times the mass of 700 times 0.5 for a total energy of, change pens there for no good reason, 113400 joules. Always again, don't forget the unit. Unit for energy is joules. Okay, calculate the acceleration of the car. Okay, this is where we might have to do a little bit of Suvat. So it was at rest at the beginning, so its initial velocity was 0 meters per second. It accelerated for 6 seconds, and its final velocity was 18 meters per second. Okay, so let's start off by just reminding ourselves of the equations that might be useful here. So we've got v equals u plus at, s is equal to ut plus half at squared, and v squared is equal to u squared plus 2as. Now we're looking for acceleration. So we're looking for a formula that has acceleration and some of the stuff, the other things that we know, and only one unknown being acceleration. So let's see. I think it's actually going to be the first one here, but let's just realize why these ones are no good. S equals ut plus half at squared. We don't know the time and we don't know the displacement. So there's two unknowns. That equation is not going to help us. V squared is equal to u squared plus 2as. Again, we are dealing with acceleration and s. We don't know them, so it's two unknowns. You can't work it out. You need something that just has one unknown. So we're going to use v equals u plus at. And we're trying to find the acceleration. So we're going to rearrange this equation to get a on its own. So I'm going to bring u across first. V minus u is equal to at. And now, because we're still trying to isolate a, let's bring the t on its own by bringing that. Sorry, let's get the a on its own by bringing the t across. So v minus u over t is equal to a. And if you remember, that's just our general definition for acceleration: change of velocity over time. So we have a change of velocity v minus u, 18 minus 0 is 18. Divided by the time it took to do that, 6 seconds, is 3 meters per second squared. Oops. 3 meters per second squared. Okay, calculate the net force on the car as it accelerates. Well, now that we know the acceleration, we know the mass of the car was 700 kgs. So let's use F equals ma, force equals mass times acceleration, to get the force. So mass of 700 kgs times the acceleration of 3 meters per second, squared is equal to 2100. And again, don't forget units, newtons. Okay, we're tearing through this one quite fast. No pun intended. The engine of the car provides a driving force of 3,000 newtons. Calculate the friction acting on the car. Okay, well, let's think about this. You don't have to draw a diagram, but I think it's going to help. So the car is accelerating with a force of 3,000 newtons. That's what the engine is provided. But something is slowing it down, and you only get 2,100 newtons of force actually resulting. The rest has been lost to friction. So the difference between the force the engine provides and the force that actually results, the difference is the friction. So the difference here is 900 newtons. So there's a force, the force of friction is 900 newtons. And finally, state one method of reducing friction. Well, you could go in vague and in general, but in relation to the car, if the car was driving on a wet surface, there'd be less friction, or if the surface was very smooth, there'd be less friction, or if the tires were bald, they didn't have as much surface area, friction would be reduced. In general, though, to reduce friction, you can lubricate things and oil them to make them smoother, and that's kind of it, really. Okay, first question, not too bad. Let's see if that holds true for the second one. I'm running out of paper a little bit here. Okay, so second question. Define the term force and give the unit in which force is measured. Well, a force is anything which will cause an object to accelerate. Okay, state the unit. The unit is the Newton. Force is a vector quantity. Explain what this means. Well, a vector has both a magnitude and a direction. Whereas if you remember, a scalar only has a direction. Okay, so that's 15 marks just for a fairly straightforward, fairly straightforward so far. So not too shabby so far. Let's keep going. Newton's law of universal gravitation is used to calculate the force between two bodies such as the moon and the earth. Give two factors which affect the size of the gravitational force between two bodies. Now again, I can always say make the logbooks your friend. And if you look up Newton's law of gravitation, you don't have to, but if you look it up, it's F is equal to m1, m2 times the universal constant of gravity divided by the distance squared. So the force of gravity depends on the masses of the objects and the distance in between them. So it's proportional to the masses, proportional to the product of the masses. like when you multiply them. And it's inversely proportional to the square of the distance between. Now, excuse my handwriting here. I'm just going to check real quick. I'm going to look at the mark scheme for this one to see if writing the equation will get you the marks. I think it might, as long as you annotate it. Okay. Not very clear on the mark scheme on that, but the two factors are the masses of the objects and the distance between them. Explain the term acceleration due to gravity. Well, the acceleration due to gravity is the force that gravity applies for every kilogram of mass, or you could say it's the change in velocity due to gravity in meters per second per second. Strange, I've never seen that before. Just ask them to explain what it is. Usually you have to derive it. Okay, an astronaut carries an experiment to measure the acceleration due to gravity on the surface of the moon. He drops an object from a height of 1.6 meters above the surface, and the object takes 1.4 seconds to fall. Use this data to show that the acceleration due to gravity on the surface of the moon is 1.6 meters per second squared. Okay, it's another SUVAT. So let's think about what's going on here. So there's the surface of the moon. We're dropping something from there. Initially, it was at rest. Before we released it, it had no velocity. At the end, it took 1.4 seconds to fall, and the distance was 1.6 meters, and we're looking for A. So again, let's remind ourselves of the equations. V is equal to U plus AT. V squared is equal to U squared plus 2AS, and S is equal to UT plus half AT squared. Now again, these are in your logbooks. You remember these are some of the derivations though that they often ask, so they're good to know, and make sure you know the derivations inside out. But let's see which one we're going to use here. We're looking for A, and we have an S, U, and T. So I don't think this first equation is going to be any good to us, because while it has what we're looking for, which is A, we don't know what V is, and we don't know, actually this might be a winner here, S, V equals U plus AT. No, it's not, because we have two unknowns, A and V. Looking at the second one, we've got V squared, which we don't know, U squared, which we do, S we do, but A we don't. So again, there's two unknowns, and you can't figure it out. It's going to be this fella, just by process of elimination. But let's make sure of why. We know what S is. We know what U is. We know what T is. We just don't know what A is. So this fella here has everything we know and only one unknown, which is the thing we're looking for. So that's going to be our winner. S is equal to UT plus half AT squared. Now we're looking to rearrange it to get it A on its own. But we can make lives a little bit easier here. Normally I'd say rearrange it and then sub in values. But because we know U is 0, if I put U 0 in here, this is just going to go away. 0 times T is just going to be 0. So S is equal, in this case, is equal to half AT squared. We're looking for A, so let's rearrange it. Let's bring the 2 across. 2S was divided by here, becomes multiplied by there, is equal to AT squared. And we're looking for acceleration, so let's bring the T squared across. It was multiplied by here, so when you bring it across, it's divided by. So 2S divided by T squared will give us our acceleration. So now let's just make sure we've got our equation rearranged. We have our values, let's just sub them in. So 2 multiplied by the distance of 1.6 meters, divided by the 1.4 seconds it took for that to happen, squared. And let's see what we get. So 1.6 multiplied by 2, divided by, and then here's where people often get mixed up with. Make sure if you're using brackets, just make sure to close your brackets. 1.4 to be squared, close bracket, gives me a value when I press SD of 1.632 meters per second squared. And that's what they wanted us to prove, that the surface on the acceleration due to gravity is 1.6. Job's done. Okay. I'm running out of paper here to work on. Give me one sec, guys. This is last week's one. I'll do the job. Okay. The astronaut has a mass of 120 kgs. Calculate his weight on the surface of the moon. Well, the G on the surface of the moon is 1.6 meters per second squared. And we know that weight is mass times gravity, acceleration due to gravity. Now again, even for such a small question, write out the equation. If something goes wobbly, at least you've shown them that you know which equation to use, even if the maths goes a bit wonky, which it can do sometimes. So the weight on the moon of this astronaut He's a mass of 120 kgs. I'm guessing that's with the spacesuit and all that. And it's times 1.6 meter per second squared. So he has a weight of 192 newtons. Why is the astronaut's weight greater on Earth than on the moon? Because there's less gravity on the moon. The moon has less mass, so it has less gravity. And finally, the Earth is surrounded by a layer of air called its atmosphere. Explain why the moon does not have an atmosphere. Well, the moon's gravity isn't strong enough to keep all the molecules of air nearby. It loses it to space. If it was to have any atmosphere, the gravity isn't enough to keep the molecules there. Okay, guys, a lot there. Again, like always, keep cracking on it. Send me what you have, even if it's not complete or it's not perfect. Send me what you have. And in the meantime, keep working through the homeworks. And if you've got any questions, don't hesitate to get in touch. Take care. Bye-bye.